Welcome back to the next lesson, talking about motors today. And so before we do, I wanted to go over some of those math problems. I'm assuming your proctor probably doesn't want to do those math problems with you, and so I will take just a moment here and do those. So the first step here is going to blank the screen so that we can kind of be writing on it. Let's get a ink color that is yellow, probably, that will be easy to see. And we will be doing numbers 3 through 5. So the first question, number 3, says a wire that is 50 centimeters long. So the length of the wire is given, length of 50 centimeters, so that's 50 centimeters, 2 sig figs. Then it says that particular one moves with a speed of, so the velocity of this particular wire is equal to 5.0 meters per second. And then after that it says through a uniform magnetic field where the flux density, remember, is denoted by the letter B, flux density, or B field of 8.2 Teslas. And so 8.2 Teslas, that's what's given here. It says 8.2 Teslas. After that, it says, so once you have that, if the wire, field, and motion are all mutually perpendicular to each other, what EMF is induced in the wire? So essentially we're looking for the induced EMF of the wire, by the way, measured in volts. Alright, so your first thought is, alright, I'll use the induced EMF formula, which is the delta phi over delta T. And the problem with that is we don't have anything measured, phi is measured in Webers, and so I don't have anything in here. This is seconds. I do actually have seconds. There was one detail I missed. Okay, and so the time that would be, the time is actually guaranteed to be a second, and I'll explain that in a little bit, but we don't actually have time given either. And so we have Webers, and we don't even have delta T right now. So as we start to do this, we have to go back to the last chapter to find that the flux linkage is actually equal to B times delta A. So that's B field in Teslas times the area of this. And so we're going to take phi. Phi is equal to the B field, so you're going to take 8.2 times the area. So I need to actually go down here and work for a little bit. Delta A is equal to. So there's an example in our book that actually talks about this, but basically you want to take the L. Let me actually do it this way. There's a way to find the area of this, and it has to do with the speed of this particular thing. So you've got 5. First of all, you take the length of the wire. That's the length of it. That's why I said L earlier. This thing is 50 centimeters. Okay. And if you put this in terms of meters, that's going to be 0.50 meters, so 0.50 meters. And then we want to take the last portion. And if we take the velocity that was given to us, it gives us 5.0 meters per second. If we multiply the two, we're trying to find area, you'd like to get squared meters, but you would get meters squared over seconds. If we could get those seconds to cancel, that'd be great. And so the way that they do this is actually they're trying to find out the rate that happens in 1 second. That's kind of a unique one to this particular problem. I can explain more about how that works, but basically the second is only there to find out the area that's covered. Now we have, basically the 1 is not even important anymore, and so we got 0.5 of that, and so the delta A, the area of this thing, is going to be 2.5, which is half of the 5 here. And so you'll have this in meters squared. So now that you have delta A, that's going to be the 8.2 Teslas times the 2.5 square meters, and you've got your value of phi. Phi is going to equal, the final answer here is going to be 80. Well, actually we don't have it, so I'd have to pull the calculator here. Give me just a moment to pull that, but you of course could do that on your own. Oh, good calculator noises. But 8.2 times 2.5, you've got 20.5 here that you'll find, so 20.5, and of course this is measured in Webers, and so that is very simple. Now notice we used the time that was given earlier as 1 second, so your delta T will happen in just a second. So the induced EMF is equal to the 20.5 divided by 1, and 1.0. And so now you have a 2 sig fig problem, so the induced EMF of this particular thing is 20 1. You'll get 20.5, but when you're done, you'll get 21, being in 2 sig figs because of that. Induced EMF, of course, is measured in volts, and so that's the answer to the first question, number 3. All right, so that's number 3. Let's go into number 4. Number 4 says a magnetic field with a flux density of 4 times 10 to the negative third Teslas. So again, B value, B is equal to 4 times 10 to the negative 3 Teslas. Again, Teslas are going to be quite small. It's perpendicular to the plane of a C-shaped conductor with arms of 20 centimeters apart. Okay, also going to be very important. And so looking at that one, we'll come back to that, but basically the length of this thing is 0.2 meters, 0.20 meters. That's the 20 centimeters put into meters. After that it says, if a crossbar moves so to enlarge the loop, and if the speed of the crossbar is 5 meters per second. So kind of the same idea. This is going to be 5 meters. I'm imagining, just 1 sig fig, 5 meters per second. And then it says find the A, rate of change in magnetic flux, and then B, the induced EMF. So the first step is going to be to find that magnetic flux, and so that is going to equal, you're going to be doing something like this. So phi over delta T is going to help you find that magnetic flux. That's B in this case. Okay, is going to equal, according to this, B delta A. And so you can write it this way, all over T, delta T. And so once you start plugging in values, you'll notice that the B value is, the B value is 4 times 10 to the negative 3. No problems there. The next portion here, you'll have the delta A value. Simply, you've got the two values. You're going to take, since we actually have the meters here, same idea. You're going to take your length, which is 0.20. You're going to multiply it by the velocity, 5 meters per second. You're going to multiply that in the 1 second so that the seconds cancel. The seconds are gone, and so you've got 5 times 0.20, and so you will get a certain amount there. Now I'll just go ahead and write this over here. The delta T is 1 second, 1.0 seconds. And so actually in this particular problem, I think we're going to make it 1 sig fig because the V at the top is 1 sig fig, and so 1 second. Moving on. So we got 0.20 times that. All right, from there you're going to say that your delta phi, your flux linkage, is going to equal delta phi over T. Delta T is equal to your B field. Okay, 4 times 10 to the negative 3, that's the B value. I'm taking this from up here now. 4 times 10 to the negative 3 Teslas times the 1 square meter, that's the 5 times 0.20 is 1 meter squared, and that is going to be 1 sig fig. And then at the very bottom here, you're going to have that all happens in a second, 1 second. Notice 1 sig fig. And so very simply, you're just dividing and multiplying by 1, so 4 times 10 to the negative third, and this is going to be finding the Webers per second. Okay, and so we're finding the change in flux in a certain amount of time. So the reason why we have this unusual fraction here is because we're looking for a rate. So we're finding the number of lines that happen a certain amount of time. So that's number 4. Let's look at number 5 together. Number 5. Number 5 is the next one here, and it says a flat rectangular coil 5 centimeters by 10 centimeters. Now we actually have normal area stuff going here, rectangular. So it has 200 turns of wire, so that's going to be N, and it's going to be 200 turns. That's the number of loops. And it says located at the Earth's magnetic field where the magnetic induction, that's B. The magnetic induction is equal to 5.4 times 10, 5.4 times 10 to the negative 5th Teslas. Moving further, it says, sorry, I'm looking at it across the way here. Flat rectangular coil 5 centimeters by 10 centimeters contains 200 turns of wire located in the Earth's magnetic field where the magnetic induction is 5.4 times 10 to the negative 5th Teslas. The coil is turned from a position where its plane is parallel to the field to where it's perpendicular to the field in the time of 0.05 seconds. So that is the delta T of 0.05 seconds. And so that's all the details that we've been given. Also the dimensions of the rectangle. And so if we're trying to find the dimensions of the rectangle, it seems to be saying that this is a 5 centimeter by 10, so 5 by 10 rectangle. And looking at the particular problem, you're going to be finding the area of that. Of course, we want to look at these as a, these are centimeters, by the way. And so I'm going to change them up and put them into delta. Basically, for this formula, we're going to use Faraday's law of induction. So the induced EMF is going to equal N delta phi over delta T. Okay, and because we don't have delta phi, the number of Webers, we actually have to use the other version of phi, which is kind of a derived formula, which is B delta A. Okay. And so that's what we're going to be using, B delta A over delta T. By the way, this notation over here hasn't really mattered yet, haven't really run into any problems with the absolute value of this, but we're going to have a positive voltage each time. So the induced EMF is equal to the 200 turns. This is going to be multiplied by the 5.4 times 10 to the negative 5th in Teslas, multiply that by the area, so we're going to take 0.05 times 0.10, that's in meters, and then we're going to take the absolute value of the top, the numerator, divide that by the time, that's 0.05 seconds. And so once you do all of that math, just making sure I'm getting that, you should get the induced EMF to be 1 sig fig. Now they're saying 1 sig fig. I would say everything I have 2 here. I have 2, oh, actually that's 1, right? Zeros to the left are never significant, so that's why this has 2. But this particular one has 1 sig fig, and so does this one. And so this will have 1 sig fig. You'll get 1.08 times 10 to the negative 3rd volts. But if we're going to do this, it'll approximate to 1 sig fig, so we'll use 1 times 10 to the negative 3rd volts. And so there's that. That is the particular math problems for this particular lesson, and so that's again, the easier math for this one. So that one is straightforward, makes sense. The area is very simple. Okay, going back into their notes, we have the motors. And so let me introduce you to page 370. Let's go to 370 to look at motors. It says motors are electric motors, convert electrical energy into mechanical energy. That's a contrast between motors and generators. Remember, if you ever run out of power and you need to have electricity in your home, you're going to go get your generator, not your motor. So what you do is you take gasoline, you pour it into the generator, of course plug it into something in your house, and you turn on the prime mover. It starts to move the gears of it, basically the motor, the armature and all of that, generates electricity, and you have that. Motors, however, are the things that spin your lawnmower. I'm using, of course, some mechanical energy put into it. Think about your car or any of those types of motors. So it converts. Notice motors, by the way, the key word is motion, motor, and generator, make. And so you have electric motors that convert electrical energy into mechanical energy. So obviously you're taking electricity and you're making it into motion. Generators, you're going to take motion and make it into electricity. Think about windmills, taking wind to spin the windmill. Think about hand crank generators, or even the one we described earlier, the alternator in your car. But electric motors are going to take that electricity, spark something, and start to move the motor based on that. And so then motors are essentially generators. In fact, if you look on the page 370, you'll notice a magnet with a loop inside of it. All the components, the armature, the brushes, the slip rings, they're all the same. All of those components will be in there. They describe something called the motor effect, and so I want to basically describe this to you the best way I can. All right, we're still on yellow, so we're going to need to go to red, I think. And so you have your horseshoe magnet, okay? Mine is a blocky horseshoe. And inside of this, I actually need to make this quite larger. I'll draw this on the screen. So here's your horseshoe magnet, okay? And so it's doing something like this. And you have a armature inside. Now your coil, I'm looking at it so it's flat. We're actually going to go ahead, and as it starts to spin, it gets polarity. It has a north and south pole. And so you'll notice we'll call this end of the magnet a north and this end of the magnet a south. Because a north is near a north, it will start to push away. There will be a deflecting force, and because south is near that, Okay, you got to also think of all the things that are involved. So because south is here, it'll start to move it this way. Again, you probably don't want to start it in this position. Let me change it because you'd see exactly the problem I was running into. Start it here. Okay, if I put the conducting loop like this in such a way that it has the south pole here and a north pole, that's how you want to start it. Okay, of course there's an attraction here, there's an attraction here, and this thing will start to spin inside of itself. Once it starts to spin though, because especially with a commutator, you will get it to a point where it will get to, by inertia, start to take that south pole, start to spin it down this way, and you will have your south pole. Now, the problem with that is if you have a south pole over here, you have a south here, you have a north here, well, all of a sudden the south will want to come back up. But a commutator, that split ring, will actually take this and make a south here and a north here all of a sudden. Now that's the polarity of the electron current. And so now that repelling continues and you essentially get motion over and over. This is what we call the motor effect. It's basically the tendency of this magnetism or this magnetic field to continue to spin the armature between it. Now again, the armature is a coil, something like this. Oh man, art skills. Something like this. Okay. And so once it starts to spin, it does get a north and south pole on either side, but we were just using a bar magnet as an example. All right, clearing this up, let's move on. So going back in, this motor effect, it's the concept that makes something a motor. It's a magnetic field that pushes current carrying wires away. And so your book starts to talk about on page 370 this concept of torque. We've talked about this in the past. Torque is applied to anything that has a hinge point, a long rod, and a force that's applied. Think about a door on its hinges, and so here's your door, you've got your doorknob, over here you've got your hinge and it's attached, okay, to the wall. Here's another hinge and it's attached to the wall. Obviously the force that you apply at the end of the door is greater. Good luck opening a door by pushing or pulling nearest the hinge. So force is greatest. Remember Greek letter, we use the Greek letter tau to represent torque, is equal to the force multiplied by the distance from the hinge or the rotating point. So torque is equal to Fr. And so in our particular lesson, we're going to talk about the torque that is found on the armature of a motor or a generator. So torque is the force exerted at a distance. That definition would be true in chapter 4 just as much as it is in this chapter. Now, torque varies as the coil rotates because at different points it's going to have more or less torque caused by the motor effect. Mentioning that. Now, I do want to mention your book talks about a couple different types of formulas. Now, when you look at the rod, if we're talking about the armature coil, looks again like this, and now it's turning into more of a fly swatter. Let's just look at it from a different perspective. Now we're looking at it so that it rotates like this. We're looking at it kind of head on. You'll notice that in the middle, it hinges from the middle point. There is a shaft that spins the armature, and so there will be a force that goes up and there will be a force that goes down that spins that. In the neutral position, torque is based on the F, the force that's applied. By the way, the force will be true and the same in both instances. And then, of course, the distance. And, of course, that distance will be the value of R, R1 and R2. Those are going to be the same. And so you will see in this particular unit that they say the torque on the armature is equal to FR1, actually force 1 and the radius, okay, plus the force 2 and the radius, or the arc that it's applied to. One of the problems is what happens when you have this thing in its angled form. And so actually in this case, now you have, if you look on the next page, you will see on the top right, you'll change the direction of the current assisting this. And so you'll actually have this thing. By the way, you'll even notice that they have inside of this kind of an X and an O on the pictures on page 371 that has to do with the direction of current. Remember, if it's got an X, it's going into the page, and if it has a dot, it's coming out of the page. But regardless, this is your conducting loop. You'll notice that the force is going straight down, but the torque is actually being applied. So force is the down vector, torque is the kind of component vector, thinking about like all the stuff we talked about before, right triangles and such. This force is going straight up, whereas the torque is again going in this direction. So torque is at an angle. So in this case, you actually use this particular formula. Torque is equal to the two forces, 2F, and then R. But the R is multiplied by the cosine because it's a component vector. There's an angle that's being used at play here. And so that formula might show up in some of the math problems we do in this unit. All right, skipping all the way over to 372, I want to talk about energy loss. It says in your book 372, a motor is basically a device for converting electrical energy into mechanical energy. Remember, energy can't just be created. You can't get it from one place out of nowhere. Notice, this conversion is accomplished with an efficiency between 75% and 95%. But in the real world, you can't get something for nothing. You'll always end up kind of in the negative. Energy losses fall into several categories. At the bearing of the shaft, energy is wasted by friction, simply just by rubbing as it spins. Resistance in all the conducting loops drains energy in the form of joule heat. That is what the heat of a wire. If you ever run an electric appliance, you'll feel the heat of it. Think of toasters. They actually run electricity through thin wires and they glow. Moreover, if the motor depends on rapid changes in polarity of an electromagnet, and if the electromagnet has a core of permeable material such as iron, energy is spent in overcoming the reluctance of the core to accept any new state of magnetization. So we need to talk about that term. First of all, energy can be lost through something called friction. The second one is electrical resistance. So just basically, if you have a wire, if we're talking through a conductor of wire, something like this, the thinner the wire, you have little electrons that are flowing through the wire. The thinner the wire gets, okay, let's get rid of these. Same number of electrons, but your wire's thinner. All of a sudden, your electrons get more cramped, and so there's friction, there's joule heat, and this thing gets hot. In fact, many of these wires that are smaller gauge like this will start to glow red hot when you run enough current through them. And so they'll just hurt. You'll probably feel the heat before you get anywhere else. There's a new term here on page 372 called hysteresis. This is the reluctance of a permeable material to change magnetization. So basically, whenever you're using, it says an electromagnet, if your core in the electromagnet takes time to energize or to magnetize, you're losing energy. It takes time for permeability to happen. Now, it's not a lot, but it is part of it. It says if the core retains one polarity when the motor requires the other, the torque does not boost the rotation as it could if the polarity were present. So it has to do with the polarity of the motor. Then we have eddy currents, and there really is a very cool video or a demonstration tool here. I might have to link that particular demonstration for you to see. Very, very cool. But eddy currents, typically we use this concept in water, but in this particular lesson it says another kind of energy loss occurs when magnetic flux within the motor induces eddy currents. These are tiny currents that produce small magnetic fields working against the rotating armature. So essentially you have your armature that is rotating in a way inside of the field magnet, and actually there are little magnetic currents, little circular currents that are influencing the movement of the armature. And so not a ton, but those things are called eddy currents, and they can slow down the amount of energy. So they mentioned this lamination. It says it at the very end of that, use of lamination. So you can actually put this lamination in there to reduce the effective eddy currents inside of this. Well, that concludes this particular lesson. From what I understand, you will have a quiz tomorrow. Your proctor will give you the page numbers for that, but I appreciate your attention, and I hope you do well on it. See you in the next lesson.